in our case, the origin will be what? 2 centimeters. Oh, you know what? Since this is actually 500 centimeters, so it's actually you know what? We could change this to make it exactly like that. We could change this to meters. And it'll be exactly like that. So if I want to solve, for example, the electric field at the origin. What's that going to be? Well, I'm going to argue that positive charges create electric field away from it. So I'm going to call this charge 1. So E1, right? So that's the electric field created by the positive is this way. But negative charges also create electric field towards themselves, right? So they add up, they end up adding. So this is, if this is the second charge, this is E2. They end up adding each other, right? So then it's just gonna be E total is gonna be K Q1 over R1 squared plus K Q2 over R2 squared.
Professor, why did he go in the same direction?
Because this is positive, so electric field of a positive is away. And then this is negative, this one is also towards it. You see? So if you remove this, what's the electric field of just the negative charge? You see? Towards. Like that.
Which is the -7?
Huh?
Which is the -7?
Yeah. You see, it's this way. Now, if I put a positive here, okay, what's going to happen? It's also away. I mean, sorry, I shouldn't say it's also away. It is away from the positive. And the electric field for a negative is towards it. So you see, if I'm here, the two electric fields add up.
Okay.
This guy creates an electric field this way. That guy is already creating an electric field that way. You see? So 9 times 10 to the 9th. And then what's the charge of this? Over 2 squared. Right? From here to here, the distance is 2. Plus 9 times 10 to the 9th times 7 times 10 to the minus 9 over the distance is 3 squared. So for this one, when you're putting the charge, you don't put a negative, right? You just add them up because we already used the fact that the electric field of this is going towards it because it's negative. So I don't want to put a negative here because then the equation will think the electric field created by this is to the left. You see? So you want to keep it as positive. And then you want to add those. So 10 to the negative 9, 10 to the 9, that will cancel. And then you're going to have here, one of the 2's will cancel. So 9 over 2 will be 4.5. And then 9 will cancel with the 9 plus 7. So 11.5 newtons per coulomb will be the value of the electric field at the origin. So can we check that with the simulation? The good thing is, yeah, look here. Oh, look at the sensor. As soon as I put the sensor anywhere I want, it gives me the total electric field at that point. 58 volts per meter. Why do they have it units of volts per meter? Because newtons per coulomb is the same thing as volts per meter. You see? So it's telling me that if I'm over here, the electric field is 58 newtons per coulomb. You see? And it's going that way. So as I approach this charge, what should happen? Should the electric field get stronger? 60, 73, 84, 100, 126, 172. Today's lab is gonna be about this. You're gonna prove this with a lab, you're gonna prove that electric field as you're approaching one of the charges should get stronger. You see, so 231, right? Why? Because when you approach one of the charges, what happens? This distance becomes very small, right? This distance is small. That distance gets big, so that one decreases. But if this one decreases very much, then this one becomes very big. Let me see. So then it's 231, 272, 300, 400, until you reach the surface of the thing, right? 1700. Now as I go away, so where's the origin for me here? It's 2 meters right here. Okay, now let's go. 16 is decreasing, right? 16, 13, 12, 11, 11 and a half. Good? Yeah? 11 and a half. Is that what we got?
Yep.
Nice, huh? Now, what should happen as I go the other way?
So if you move it closer to the negative charge, then they would be faster?
Let's go here. 11 and a half, 11.6, 11.7, 12. Is the arrow getting bigger? Yeah, the electric field is getting strong. The electric field is getting strong. Whoa, 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 whoa. Okay. So it's reaching about 3,000.
Can you pass the sensor through more than one more time? So.
Oh, it should blow up when I pass the center. It's like 26,000. Okay, now if I go here, 1,300, 14, 1,200, keep going, decreases. Okay, why is it to the left if you go on that side? Why is it to the left? Well, because this guy creates an electric field towards it, E2. That guy creates an electric field, what? Away from it. But which charge is stronger? E2 is always stronger, right? Because it's also a bigger charge, right? And you're closer to it. So if E2 is always going to be bigger than E1, so that means over here, the electric field will always point that way. It will never switch on you. Let me see. So it's always going to be to the left, and it's going to keep getting weaker. Okay? How about on the other side? So it gets weak, then it gets strong. Okay, now which direction is it? To the left. Why is that? Right, so over here, E1 is this way. This is positive, right? So E1 is this way. Which way is E2? That way, towards the negative, right? So when I'm close to this guy, it should win. So E1 should beat E2, right? As I go farther, E2 might have a chance because it's a bigger charge, you see? So what should happen there? Goes weaker. 8, 7, 6, 5, 3, 2, 1. somewhere it should be 0. Oh, we ran out of space. So what should happen eventually?
You get out of the field,
Huh?
you get out of the electric field, right?
Yeah, after that, after there's a certain point where the electric field is 0, after that, it should go back, that guy should win. So it should be like this, like that. So over here, it should be like this, like that. Until the point where the E field is 0. Then it goes like this. But here it's very weak, you know. So we would have to go to the simulation, we would have to go on that side. I'm trying to transition over here. Okay, let's see. Electric field, 0. It's quite a while until it's 0, huh? It's gotta go all the way, maybe, well, that's one of the questions we gotta solve, is where's the electric field 0? Okay, the other cool thing that this one also could show is the voltages. I could go anywhere and it would show me the voltage. So that's when we come back to the 2 chapters later. It's saying that the voltage here is 22 volts. So now look, even better, if I click here, I can go like this, click, click, oh my God, this is such a good program. What is it showing me here?
Showing the voltage at those points.
This is today's lab. If the campus ever closes because of the coronavirus, we could do this virtual lab online. So what is it showing me? Lines of equal voltage, equal potential lines. All along this line, you got the same voltage. You see, you got positive voltages, then you got, eventually it turns into 0 volts, then you got negative voltages. So near the negative charge, you got negative voltage, equal potential lines. So if you drag this, look, if I drag this, I can't drag it outside of that box. Look, it's forced to go around that circle. What does it mean? Everywhere on that circle, the voltage is 22 volts. This one, everywhere on that circle, the voltage is 12.4 volts. Everywhere on that circle, the voltage is what? 7.4 volts. So if that's the case, let's say, what would be the electric field between these 2 equal potential lines? What's the equation for electric field and voltage? Remember I said what's the units of electric field? Volts per meter or newtons per coulomb. So if I want to find the average electric field, I do change in voltage divided by distance. So if I want to know the electric field between here and here, I do the difference of the voltage, 22.4 minus 12.4. That's gonna give me the average electric field. 22.4 minus 12.4, no, 22.0 minus 12.4, divided by the distance between those two lines, which is gonna give me, take my meter stick, 23.4 centimeters, the distance between them. Okay. So in terms of topology of a map, equipotential lines are showing you, like, imagine this is a mountain, they're showing you lines of equal height. That's what equipotential lines are. And the electric field is showing you the steepage of the road. So it's taking that height minus that height divided by the distance that you have to drive to get to that height. So the electric field is saying how steep the road is, whereas voltage is showing you the lines of equal height, elevation. You see? So then the distance between them, 0.234 meters. No, this was 22.0, I think.
Yes.
So then that's gonna be 9.6 divided by 0.34.
41 point.
41.02
02.
volts per meter. Now, can I check that with the app? Can I take the sensor? Can I take the sensor and go put it there in the middle? Between those 2 points. What is this telling me? 42.7? Is that what we got?
41 point.
Gotta get that. Do that again?
Oh my God, it worked. I was not sure it was gonna work. I was like, my heart was beating. Oh yeah. The electric field in the middle of two equipotential lines is the average of the electric field in that region. So it's the change of voltage of the two equipotentials divided by the distance, 42.7. You can see. That's exactly what you're gonna do in lab 5. Okay, so now let's go to question number 2. Let's erase the voltages. Put the voltage meter back in its little place. Okay, what's the second question was it asking? Where on the x-axis is the E field 0? So we expect the answer to only be possible in this left region, right? Where the 2 nanocoulomb has a chance of matching this. So what we're gonna say is somewhere how do we set that up? So somewhere over there, the electric field of the E1, which is this way, and the electric field of the E2, their value, absolute values have to match, right? Absolute value of E1 has to equal absolute value of E2. So K Q1 over R1 squared KQ2 over R2 squared. So the K's canceled, then you put the charge 2 nanocoulomb over, so the coordinates of that point are x0, right? So the distance from there to there is gonna be this just simple distance equation, x plus 2 quantity squared. And then the charge here is gonna be 7 times 10 to the minus 9. X minus 3 squared. And then the 10 to the minus 9 cancels, cross multiply.
Could you explain the distance thing?
The distance is just gonna be the distance between a certain random point x0, x minus negative 2, right? Which is just x plus 2. And then x minus 3 quantity squared.
And whatever x value you get, you assume it's negative? since
Well,
it's- or-
this equation, when I solve it, might give me 2 answers. So I'm only gonna accept the answer that is less than negative 2.
Okay.
Yeah. The other answer I'm gonna throw away. So x squared minus 6x plus 9, x squared plus 4x plus 4, multiply the 2 in. 7 minus 2, 5x squared, 28 minus plus 40x, 28 minus 18, 10. Right? Yeah. Then divide everything by 5. And then quadratic equation, negative b plus minus square root of b squared minus 4ac over 2a. Negative 8 plus minus square root of 64 minus 8, 56 over 2. So the other answer, I think, if you do square root of 56 minus 8, that gives you, it doesn't give me the answer I want. I want the negative one option. So x negative 8 minus square root of 56 over 2. Negative 7.7. So that means it was 5 meters to the left of this guy. That's why our space ran out, right? 5 meters was, where did you put the gold base?
What?
Yeah, 5 meters is about here.
Particular one.
Yeah, it's gonna be somewhere over here. We're almost there.
I like to.
Where the electric field is gonna be 0. After that, the electric field will switch. Questions someone had? Okay, what was the next question? We're on the x-axis. Oh, the other question was, in between the 2 charges, at what point does the electric field reach its weakest? Remember, here and here it's very strong, and then somewhere here it probably reaches its weakest value. At the origin it was 11.5, but that's not necessarily its weakest value. So how would we find that point? So we're done with that one, right? The negative 7.7 is where the electric field is 0. So C, could we come up with a general equation for the electric field in between the 2 charges, and then take the derivative, set it equal to 0 to minimize it, right? So in between the 2 charges, the electric fields add up, right? So it would be it'd be basically the equation we just had, k q1 over r1 squared plus k q2 over r2 squared. So the general equation will be the sum of the two electric fields. 9 times 10 to the 9th, 2 times 10 to the minus 9, x plus 2 squared, plus 9 times 10 to the 9th, 7 times 10 to the minus 9, over x minus 3 squared. And of course, then this cancels, this cancels.
Shouldn't it be to the first power?
Which one?
It shouldn't be squared, right? Or it should- I know it should.
No,
it
electric
should be-
field
it
is
should-
square.
yeah.
When we get to voltage, then it's the not square. So then it's gonna 18 over okay, now we can take the derivative of the electric field with respect to x. And then what would that be? The derivative of this will be, it's x to the minus 2, right? Negative 2 comes down. So it's 18 times negative 2, and then you subtract 1 from the power, so it'll be negative 3, right? Over x plus 2 cubed. Then plus 63 times negative 2 over x minus 3 to the third. Then you take the derivative of the inside, but that's just 1. So you want this thing to be 0. I guess you could do, the 2's cancel, so you're left with 18, negative 18 over x plus 2 cubed is 63 over x minus 3 cubed. Cross multiply. Could you cube root both sides? Oh, there's a negative here, huh? So if you cube root negative 18, and then this is gonna be x 1/3, and then this is 63 to the 1/3, then x plus 2. And then you should be able to solve it, I guess. Take that, distribute it. A negative 18 is cubed rootable, right? Because it's not a square root.
Will be 3
But it's
cube
not a perfect number, but it is cubed rootable because you could take the cube roots of negatives, but not the square roots of negatives. Yeah. Yeah, you should be able to now distribute that in, solve for x. And the answer you get hopefully will be between negative 2 and 3.
How did you get a cube root?
You got what?
What did you say?
When you take the derivative of something 1 over x squared,
Second.
you always do like this.
I see. Turn.
This is thinner.
You first write
Does it
that as
go
x to the
yours?
minus 2,
I
then you
put
take its
that.
derivative, negative 2 x to the minus 3. Then you can bring it down to the bottom.
For sure.
Yeah.
It should be negative 0.0145.
Negative 0.0145 meters. Oh, that's why when I was doing it, So it's almost where we had it at the origin. That was almost like the weakest. And now if I want to know its actual value, I take that and put it back into here, and then I can find the exact value of that. Put the negative. It should be close to 11.5, but slightly even smaller than 11.5.
Well,
Yeah, I get like 0.01.
Yeah.
11.5?
oh, no,
11 point, but it should be less than 5, right?
Point
Yeah, it's
four.
498.
Okay, good. Newtons per coulomb or volts per meter, either one is same. Okay, next question was, where on the x-axis, so there were a bunch of questions that was all had to do with the x-axis. Where's the E field 0? What is it equal to at the origin? Where is it weakest? Then the next one can be, where on the x-axis is the E field equal to some value? Okay, so in this case it asks, where on the x-axis is the E field twice the value at the origin? So that would mean, where on the x-axis is the total E field twice the origin? That would make it 23 newtons per coulomb. So we would expect it to have probably 4 answers, over here and over here, since the E field gets stronger as you approach this charge, and then stronger as you approach that charge. So maybe one answer here and here, and maybe one answer on the other ends, where it's 22, when it's 23. So we could take this equation, since this is the total E field in the region between them, right? And then just set it equal to 23. So instead of taking its derivative, this is for the region between the charges. And now we're setting this equal to 23 newtons per coulomb. On this one, probably the best way is just put it into solver instead of trying to manipulate it.
Is this for question number part?
This was D. So you just go to solve 18 divided by x plus 2 squared plus 63 divided by x minus 2. Oh, the TI-89 gives you 4 answers. So it gives you all 4 at the same time, but this one and this one you have to reject and just accept these 2. Why? Because this electric field equation applies when you're in the region between the charges. When you're in the region between the 2 charges, the electric fields add up, and then their sum must equal to 23. So only accept the two possibilities, 1.029. Let's see if that works. 1.029. Would be 1.029 would be 1 meter. Negative 1.029 would be 1 meter from here, right? So if I take my sensor, that's about 1 meter. So if I take my sensor there, it should be about 23. Yep, right there, 23. 23.0 volt per meter. And if I go down the other side, there should be another one where it's 23. Okay. Okay, how about in the two regions this way, how do we set up the equation? Right? Here, it's the difference of the two electric fields, right? It's the difference of the two electric fields, because when you're on this region, this guy's electric field is to the left, that guy's electric field is this way. The difference of the two. Here, it's also the difference of the two, right? So what we could do is put a minus here. And then set them equal to 23. So if we go to RTI and just change the sign to minus,
Oh, I don't know how to use that one. I heard it before. I don't get it.
You would specify how many regions, how many points you want for this, right?
okay, I put a negative 2.85, negative 1.17, negative 2.8, oh, it just gave me 2. So when I did 18 minus, it gave me negative 2.85, which is here, and negative 1.17, negative 1.17, which is here. So which of those two? It's only giving me 2.
That one.
So it's this one, right? That's the one that I want. So now,
That's E.
so this is in the left region, this left region. So left region, then it's gonna be negative 2.85. The other one I'm not accepting. Let's see if that works. If I take the sensor to,
Wait, what?
.85 is not even, it's not even a meter, huh?
Because the equation
This is,
is
this is a meter.
the force
So
is.
even before I reach a meter, come on, get to 23, get to 23. Come on, do it. Right. There. Yeah, 23. See, before I
Testing
get
this
to
region,
meter.
so it has to be
Before I get to meter. But of course, the electric field is that way, because this guy's here.
Yeah, because
See.
the distance might be negative.
So now how do I get the other answer?
It's gonna be right here. But that's for this one.
Then I could put a positive and negative,
Okay.
right? And that should give me that answer.
Is this for part E?
Which one was the part that I forgot the letters? That was asking where
This
on
is
the
part D.
x-axis is the electric field twice? Yeah, we're still on that one.
Twice.
So now I'm gonna switch the signs and put it on Now I'm gonna put this positive,
First is positive, then it's negative.
and then put a negative on the other one. It didn't give me an answer. It give you an answer? It said, I'm just tired. You wore me out today.
Mhm.
60.
I got a 4.64.
Yeah, you getting it?
Yeah.
Yeah, 4.64. The one, you get another one here and here, but only accept that answer. So right region,
For what?
This one.
plus 4.64, which is 1.6 meters. So over here, it's very close to this guy. It's kind of weird how that works. But then over here, you have to go further away. Oh, because this is so strong. Yeah, this charge is so strong. You have to go further away from it in order to give you 23. Over here, it's probably so strong. So if you take the sensor and go all the way there, see how strong it is? 400 volts per meter. 400. So you have to keep going farther and farther away for it to drop to 23. Okay, that makes sense. So it's not symmetric. Okay, now the last question, E, says, now what's the force on a charge that you place at 1, 4? So at some random point. At some random point, 1 and 4, you place another charge. Well, that question is similar to saying what's the electric field at that point. So what you could do is first find the electric field there, the total electric field. And then once you find the total electric field, you can then find the force on any charge where you place it, you see. So force question and electric field questions are similar. You can find the E, then you can find the force. Okay, so what should the answer be for the electric field? At 1.4 meters. You know what? I gotta bring this down. So let's go over here. So where would 1.4 meter be? Let's see here. It's showing me here before. The distance between them was
5.
2.
What?
Oh, no. Okay, 1.4 meters is right there. If I take my sensor there, what's the electric field? Can't see it? 3.48. Oh.
There's supposed to be another charge thing.
Huh?
Yeah.
There's supposed to be another charge thing.
Yeah, but I don't need that other charge in order to find the electric field there. You see what I'm saying? But once you tell me the charge, I can tell you the force on that charge.
Mm.
So here's 4 meters. 4 meters. Okay, so it looks like the answer is the total electric field is like this, because we would expect the total electric field will be, if I draw the if I draw the electric field configuration of a positive 2 and a negative 7, I expect the lines to look like this. But the negative 7, since it's stronger, it makes these lines go up and then come back down really quick. If it wasn't that strong, these lines would continue going up and then come down. You see? So it's gonna kind of go up and then immediately come down, you see? It's a little bit lopsided. You see that? Well, that's a nice shape, like egg, right? So 4 meters would be where? This is -2, 0. Actually, 1, isn't that midway? No, 1 is 3 meters from here, 2 meters. Oh, it's a little bit closer to this guy, right? It's 1, 4, somewhere here. So I expect the electric field to be like that. You see, the total electric field, I expect it to be down. And what is that? What is it telling us? According to there, the higher up you go, the more down it is. Do you see that? If I'm here, as I go up, if I'm here, it's kind of like that. But if I'm all the way up there, so it's probably even more. So according to the simulation, the answer is 2.9 volts per meter at -51 degrees. 2.91 volts per meter at -51 degrees. Negative means like this one, right? 51, below the x-axis. Right, so let's see if that's what we get. Okay, so how do we do it? Are we more accurate or the simulation? Always we. Because somebody programmed the simulation the way we're about to do it, right? So if they programmed it a little slightly off, right? So how do you do it? So you say the electric field at any point is the sum of the vector electric fields created by each charge, right? So this one creates an electric field. If it's a positive, which direction does it create an electric field? Away from it, right? E1. This guy, negative charge, towards it, and it's gonna be much stronger, right? E2, since I'm closer to it, and also it's stronger charge. So now I'm gonna take this, define this charge angle as alpha, define this as phi. So now I'm gonna say E1 cosine alpha plus E2 cosine phi will be equal to E total in the x direction. So take the cosine of this and the cosine of that. That's their x components. Their x components will add up. And then E1 sine of alpha the vertical component and the vertical of that, they will cancel. Minus E2 sine of phi is E total Y. Okay? I think some of you were waiting for this topics to start. From the beginning of the semester, you were like, I have to just tolerate thermo,
That's me.
because this is what I'm really here for. And now you're like, yeah. I can see the smiles on the faces. That was child's play stuff, right? Now the tests get really hard. In a different way. Okay, so now what's the E1? 9 times 10 to the 9th times the charge, 2 times 10 to the minus 9, divided by that distance. Right, so what is that? This is 1, 4. This was negative 2, 0, right? So this distance would be 3 meters. 4, oh, 3, 4, 5, right? I like that. So then the distance R is 5. So you just do 5 squared. So KQ over 5 squared. Then cosine of alpha, it's going to be the same as this alpha, right? So since this radial line from here to here, that alpha and that alpha are the same.
They're like
So
similar.
cosine of alpha is 3/5.
Is that like similar triangles?
Yeah. It's like an extension, because this line and this line are two parallels. Two parallels cut by a transversal. You see? So this angle and this angle are the same.
Okay.
You got a charge here, creates an electric field there. You see? So it's like two parallel lines, transversal. Alpha, alpha. So cosine alpha is 3/5. Plus E2 is gonna be 9 times 10 to the 9th, 7 times 10 to the minus 9, over, what's this distance? This is 2.
2, 4.
Right, so then that's square root of 20.
2 square.
So square root of 20 squared times cosine of phi, and then phi will be the same thing as this phi.
That's alternate.
Alternate interior angles. So cosine phi, 2 over root 2. Root 20. Okay, so this cancels, so 18 over, 18 times 3 over 125, 5 cubed, plus 63 over 20 times 2 over root 20. That's gonna give you E total X. Okay, let's calculate that. $1.84. Now E total Y, you subtract them. So some of these will be the same. So you can say this part will be the same, E1, right? So you're still gonna get 18 over 25. But except you're gonna do sine of alpha, which is gonna be 4 over 5. So instead of 3 over 5, you're doing 4 over 5. Then you're subtracting E2, which is still this guy, 63 over 20, times sine of phi, which is gonna be 4 over root 20. Okay, so slightly, it's gonna be 72 over 125 minus 63 over 5 root 20. Negative 2.24. Makes sense, right? Because this guy is gonna beat this guy. So that means when you put this to the tip of that, you're gonna get the electric field like that. And that's that electric field that I drew in green, right? It's the sum of the two electric fields at every point that gives you the electric field at that. So according to the app, we should be getting something like 2.91, okay? So one more step to do for us to check our answer, right? So if the electric field in the X, this is the electric field in the Y, right? So if the electric field in the X, E total X, is coming out, did I draw it? I didn't write it anywhere. What did I get?
Which one?
E total X, I never wrote it anywhere.
Oh,
What was it?
1.84.
1.84. So E total X is 1.84, then E total Y is negative 2.24. Right, so then E total would be this squared and this squared, add their squares and square root them. 1.84 squared plus 2.24 squared, square root 2.89. 2.898, which is more like 2.9. E total 2.90 volts per meter. Ha ha ha. Let's see. This is a great app for you. You can practice too. Just make any charge and then practice getting the electric field anywhere, you know. Great preparation for a test. Okay, how about the angle? 51 degrees is telling us. How do we test that?
Tan inverse.
Tangent of this angle, call it theta, 2.24 over 1.84. So take the inverse tangent of that, right?
Mhm.
50.6 degrees. And you can just put a negative because it's below the x-axis. So as you drag this here, you can kind of see how the angle's changing? Now it's positive angle. So you should be able to go even outside of the two charges. Let's say on the test I ask you something like that. On the left of the two charges. Doesn't have to be in the middle. Prove what the electric field there is, you see. So anywhere you should be able to get the answer. Even somewhere here. It's telling you 150 degrees. So let's do that as a practice. I'll give this to you and then see if you can do it in the SI section. Let's see here. Okay, 1 meter to the left of the positive. And I think that's a half a meter up. Yeah, half a meter up. So 1 meter this way, half a meter up. That make it what? Negative 3.5.
Positive or negative charge? It doesn't
Oh,
matter.
oh,
Actually,
you know
it
what?
doesn't
We
matter.
just found the
Yeah,
electric
yeah.
field at this point. We
Yeah,
didn't even
doesn't
find the
matter.
force.
Yeah.
So the app is telling you the electric field is 12.3, right?
Yeah.
Volts per meter. And then the angle is saying 150.7 degrees. So see if you can get that. Now, what would be the difference of if a force question? Once I've given that the charge there, what was the charge? I think something like negative. In part E. Negative 3 nanocoulomb charge. Okay, so now what's the difference for a force question? The question said, what's the force on that charge? How do you do that? You have to start all over again? You have to say, oh, the force of this on that versus the force of this on that, break into components. No, you already did the total electric field there. So the force on that charge will be the total electric field times the charge of that third charge. So the magnitude of the force on the third charge will be what? Its charge is 3 nanocoulombs times what's the electric field there? 2.9 volts per meter. And what is that? 27 to 8.7 nanonewtons. That's it. Because remember, volts per meter is the same thing as newtons per coulomb. And that third charge is 3 times 10 to the negative 9 coulomb. So coulomb cancel, and then this is a nano. So just 3 times 2.9. The force on that third charge is 8.7 nanonewtons. Now, what's the direction of that force? Okay, the electric field there was in this direction, right? Now the charge you're placing there is a negative charge, not a positive charge. If it was a positive charge, what would be the direction of the force? It'd be the same as the direction of the electric field, negative 51. But if it's a negative charge, the force is this way. You see? Negative charges feel a force opposite to the direction of the electric field there.